Hi, in this video I am going to quickly revise you the topic of vectors. So we have vectors in physical world. We in physical quantities can be either scalar or vector. So scalar quantities has only magnitude. Example of scalar quantities, we know its mass, time and various other scalar quantities, whereas vector quantities has both magnitude and direction. So we are talking about vector quantities. So a vector can be represented as a with a bar like this on the top. So this symbol here tells that this a quantity is a vector quantity. So if I take this as vector a, so here what I have is, this is the initial point of the vector and this is the final point of the vector, which is called tail, this is called cap symbol. So here if I divide it in units, if I take this as 1 unit, we have 1 unit, we have 2 unit, 3, 4, 5 and 6. Suppose this vector a is of magnitude of 6 units. So we define a unit vector as unit vector in direction of a. This is unit vector in direction of a. It is represented as a cap. E is nothing but vector a by that of magnitude of vector a. So if I take this vector in 3-dimension space where it's x, y and z, here if I take this vector as this, I take this vector as a with its initial points x, y and z, and here I have this as here x1, y1, z1 or z1, and here I have this as x2, y2 and z2. So this vector is nothing but, can write this as position vector of first point r1 and position vector of second point r2. Can write this vector a as a will be equal to, here vector a is x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. So what does this I cap, j cap and k cap represent? So here what does this x, y, z, x1, y1, z1 and x2, y2, z2 represent? Let's talk about it. So here if I take a point here, for that let's take a point here in x, y and z direction, and I take this point as x1, y1 and z1. from the origin I draw a position vector to that point. I representing it as r1 position vector. So to get the components in x, y and z direction, to simplify it, I am taking perpendicular to x axis, perpendicular to y axis and perpendicular to z axis. So what I get x component as x I cap, this is the what you say, the x component of the position vector x I cap, and here I get this as y j cap, and here I get this as z k cap. So I cap is nothing but a unit vector in the direction of x axis, and here j cap is the unit vector in the direction of z axis, and k cap is a unit vector in the direction of z axis. So that means magnitude here more, if I write I cap in this mod, that means it's the magnitude of I cap. So magnitude of I is magnitude of j cap, that is magnitude of k cap, that is of 1 unit, and these three I cap, j cap, k cap are I cap, j cap and k cap are mutually perpendicular. So if I take this point here, I take this point as x2, y2 and z2, and take this vector from a particle moves from x1, y1, z1 to x2, y2 and z2. So the motion of that displacement I am representing as this. So this is vector A, and position vector of the final point is r2. Here I get r1 as, here r1 is nothing but I get this as x1 I cap plus y1 j cap plus z1 k cap, and r2 from similarly I get r2 as x2 I cap plus y2 j cap plus z2 k cap, and we know that displacement is nothing but final minus initial. So here that's nothing but r2 minus of that of r1. So here we get this as x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. So it's nothing but vector A. So I am writing x2 minus x1 as a1, this as a2 and this as a3. So vector A is nothing but a1 I cap plus a2 j cap plus a3 k cap. If you are not getting this, then no problem, we will solve questions regarding this to make us better understand. So next we have the magnitude of A. Magnitude of A is nothing but a vector, we have this unit vector in direction of A is nothing but a vector by that of magnitude of A. To get this magnitude of A is nothing but square root of a1 square, that is x component of vector A, plus a2 whole square, that is y component of vector a, and a3 whole square, that is z component of vector a. For simplicity, I am writing this as x square plus y square plus z square. So if we want if I take two vectors, this as vector a and this as vector b. So if I want to add these two vectors to get, I will get the resultant as this is vector a and this is vector b. It is the angle between vector a and vector b is, let's suppose, take it as theta, and the resultant will be the diagonal of the parallelogram made by these two vectors. So it's the diagonal here, it's the resultant here, vector b is resultant. Can we find what is the magnitude of that resultant? Yes, we can. Here I take this as vector a and vector b. Angle between a and b is theta, and suppose angle between a and this resultant is phi. So for that, let's do this one. I take this as theta is a b c d and e. So what I get here, if we solve this, is resultant of a vector plus b vector, the magnitude of this, say r vector magnitude, is equal to under root of a square plus b square plus 2ab, that of cos of theta. See, so here we can say that r is maximum when this cos theta is equal to 1. So here r equals to a square plus b square plus 2ab when cos of theta is equal to 1. When is cos theta 1? When theta equals to 0. That means for two vectors in the same direction, we have this as a and this as b. If we add this in the same direction, we get the resultant as maximum. Whereas if we take cos of theta as -1 for two vectors which are opposite in direction, we have vector a and similarly we have vector b. So resultant will be this. So this is about addition of vector. We have already done the resolution that if a vector is in 3D plane, it's in xy plane. So we have to just draw perpendicular to x and y axis to get the x component and y component of that vector. So let's talk about the dot product or scalar product. So it is a product or multiplication between two vectors, or product between two vectors whose product or resultant is a scalar quantities. If we take work is nothing but force dot product of d. So dot product a vector A dot vector B is defined as A magnitude of A times that of magnitude of B times that of cos of angle between them. So here if I take vector A as A1 I cap plus A2 j cap plus A3 k cap for a vector A here we have in 3D space. Let's draw it here. This is in x, y and z. We have vector here A and we have a vector here B. We want the resultant, and this is the angle between vector A and vector B, which is theta. And we have vector B as B1 I cap plus B2 j cap plus B3 k cap. Then what will be the magnitude of this? That's nothing but, if you want the magnitude of A dot that of B, you have to just multiply this individual A1 B1 plus A2 B2 plus A3 B3 to get the magnitude of it. So here also it has no direction, so this A1 B1 A2 B2 is nothing but A B that of cos of theta between them, that is A1 B1 plus A2 B2 plus A3 B3. So if we want to find the cos theta between them, angle between them, we have cos theta as, can write this as A dot B by its magnitude, no mean to that, so it's it will be a scalar obviously. So we have this as A dot that of B. If we add this mod or remove this mod, that doesn't affect this. So you have seen that here cos of theta is there. So cos theta is maximum when theta is equal to 0 and minimum when theta is equal to 180 degree, and here cos theta is 0 when theta is equal to 90 degree. So if we take this vector here, if we take this vector A and vector B, we want to find a cross product, then there will be no work done. If we take force in this direction and we have this velocity as this direction, and then the displacement will be 0, or sorry, displacement will, the work done will be 0. If we take to understand this, if we take a circular motion, we have this, right? Circular motion we have. In this circular motion we have this centripetal force, I'm taking it as F, and displacement here in this direction, displacement, let's say dr. So work done at this particular instant is 0, as it's rotating and coming back to the same position. So work done in total movement of this particle in circular motion is 0. So we get this dot product of vector A and vector B as A B cos of theta, and if a vector A is dot product with that of A vector A B plus of that of vector C, you can write this as A dot of B plus A dot of C vector. And again, if we have this A plus B dot of that of B, sorry, let's say A minus B, A minus of that of B. So here we get this as, we can rewrite this as A dot A, sorry, A dot that of A minus B plus that of B that of A minus B. Again, if we again do it, we get this as A dot of A minus A dot of B. Here we get this as B dot of A minus B vector B vector B. So here we get this as A square mod of A square, and these two will get cancelled, minus of that of B square. Oh, one thing I forgot, that if I take A dot of B, it's same of that of B dot of A. So let's go to the cross product. You must have somewhat understood what dot product is. If we solve different problems, many problems, we will better understand it. So we have cross product. Here in this cross product we have vector A and vector B. Here this, let's say this is vector A and this as vector B. So the cross and the angle between it is theta. So the cross product between vector A and vector B is the resultant. The resultant of this will be normal to that of vector A and vector B, plane of vector A and vector B. Here it is represented as A cross that of B is equal to magnitude of A plus magnitude of B, that of sine theta times that of n cap, where n cap is the unit vector in this direction, normal direction. So to get the equation, if we have A as A1 B1, sorry, A1 I cap plus A2 J cap plus A3 K cap, and B as B1 I cap plus B2 J cap plus B3 K cap. Here what we get here, A cross product that of B is, let's do it here. So A cross product that of B is nothing but the determinant of 3 into 3 matrix I cap J cap K cap. Here we have A1 B A1 A2 A3 and B1 B2 and B3. So if we solve this, we get here as I cap A2 B3 minus A3 B2 minus of that of J cap, that is J cap times that of A1 B3 minus A3 B1 plus K cap, that of A1 B2 minus A2 B1. How did I get it? Just solve this determinant. We will get this one. So what will be the magnitude of this vector? So magnitude is nothing but again under root that of 2b3 a3b2 whole square plus same a1b3 minus a3b1 whole square plus that of a1b2 minus a2b1 whole square. This is the magnitude of resultant R. So in the diagram here we have this A vector and this as B vector. So the resultant will be this normal, that is I am writing it on this page. This is not this. Now this is resultant, let's say R vector or n vector, and n cap is its unit vector. So A cross that of B is A plus B plus that A into B, that of sin theta and cap. This is angle theta. Sin theta is nothing but we can write this theta, we have this this is vector A, this is vector B, we have this angle as theta. Same we do this here. We have this direction in y as we have this, here is theta, here is theta. We have this as cos sine of theta, so we have here as p of sine theta. So its maximum when this sine theta is equal to 1. We can see here. If we take two parallel vector and have a vector product in it, so this resultant will be the maximum resultant. It's out of paper. Out of paper means this one, right? Resultant R will be the maximum. And if the sine of theta is 0 degree, say this 0 degree to vector, then resultant is 0. And when the sine of theta and angle theta is minus of that of 90 degree, if we take this vector A and this as vector B and angle between it, both of this is minus of that of 90, then resultant will be inside the paper. So this is resultant will be this inside the paper, that is n vector. So in next video I will solve some of the problems related to vector to make it look clarified.